Huh.
But it's taking forever. So if it doesn't finish by class, I was wondering if you wanted to look over it with me and you
Sure.
can see if there's something that stands out.
Yeah, it should. And how do you do the theta integral?
That's a command in MATLAB. They have an
Oh,
integral
I see.
function, and you just specify the variable.
I see.
and-
Stuck. Oh, this is all set. Homework 12. Oh, yeah, I have to put this up today. Second Wednesday. But today we will do stuff that is necessary. And the final exam. So it is take home. And it is due by 4:45 p.m. Available around December 5 or 6. One. And today is the last day of physical classes. Next week we will have classes, but pretty much I will be here. You guys log in from wherever you are. And is there anything else I have to say? Can think of that you might need. Something so, yeah. And contact me on email if there is any questions. Okay, so today we want to, remember we have done a couple of conservation equations. So we have some added equations to our list. So we have Maxwell's equation. And they look like this. T is equal to, let me write it in row of R2. And then we have zero and we have the cross E R2 is equal to time derivative magnetic field and finally cross. And we added some equations. So this is Maxwell's equation. And we also have, so maybe just for completeness, we also have Lorentz equation, which is an independent equation, independent of these four equations. And that is actually, I should, before I write that, I have D is equal to epsilon naught times E, and E equal to mu naught times H. We have Lorentz equation, which is best actually written in terms of as a force density. So it is F of R comma T is equal to rho T times the electric field plus J T crossed with the magnetic field. These two are independent set of equations. We then derive some conservation law. Let's call this conservation law. And these are derived from these Maxwell's equations. And those were dt rho of T plus this is J. And I write specifically the R and T because I want to talk about this in Fourier space or the frequency space very soon. So this is d by dt of u T plus flux of energy that's equal to 0, and we have all of this machine. Equal to right? That's pretty much this, and this is a full set of equations we have. And for completeness, I also have u of RT equal to half epsilon. That's better. So E divided with D plus H divided with E. All these are R and T, the left hand side, so it decides what is the right hand side. That's E crossed with H. G is equal to E crossed with E. And finally, T. The dyadic U minus of dyadic. This is energy density, flux of energy density, momentum, flux of momentum. So we would now like to, most of the time what happens is that when you're working with experiments involving light, light is you usually use a monochromatic wave, and those are frequency dependent quantities. Most of the optics that we do, all the devices, other things are frequency dependent quantities. So frequency is a Fourier transform of time. So let's begin today by dealing with Maxwell's equation itself in the Fourier world, and we want to actually then start working with conservation laws in the Fourier space, and the difference primarily is that all these quantities here, like Maxwell's equations, are all single field, right? In each equation, you have one field. Right? Each term has only one field in here, but in the force and the conservation equations, you will accept for this charge density equation, U has two pieces. So U has two fields in it. So there are bilinear combinations of the fields, and so when you Fourier transform it, that is a you have to do it in a proper way. We have to identify the right step. So let's see what happens with Fourier space. Let's begin by just doing one derivative. That's the so in the Fourier space, so if you have electric field in the time space, its Fourier components are, so there is space and time. So let me begin with just Fourier transforming the time piece. So time becomes frequency, and this is e raised to minus I omega t. And now electric field is not in the time, it's in frequency. This electric field function will be independent, it's a different function altogether, but we will use the same letters just to signify the fact that it is a Fourier dependent quantity will be given by the dependence in there. In principle, this functional dependence is different from this functional dependence. So it should be tilde, for example, or subprime field. The Fourier transform of this, if you want, or Fourier inverse of this, if you want, is equal to t times exponential of I omega t times of t. These are the Fourier transform of each other. So the language would be these the omega dependent quantities are the Fourier components of the electric field in the time space. That's good. So what is before I proceed, actually, I have to do one more thing. This is just in time. Let's do this in spatial space coordinates also. So I'll now do one more. R of t. So now this is already Fourier transformed in time. So the Fourier transform in space also. This is d cubed k. So one wavelength for each of the space components. That's 2 pi cubed. And then there is, of course, frequency there. All these are running from minus infinity to plus infinity, or if you're using any other coordinate system, they'll go over the whole space. And that's exponential of I, k dotted with r, minus of I omega t. Notice the plus and a minus sign. That's because in relativity, time behaves slightly different than in space. So that's to, it doesn't matter whether you choose a plus or a minus sign, but we'll keep it in this form so that there is a Lorentz invariance that is very useful when you're doing relativistic transformation. So it's not necessary to choose this to be positive. It could have been negative, but it's a choice. For example, here it could have been negative also. It's perfectly okay. Since it's an integral, you could have chosen it either way you want. And now the electric field depends on k and omega. And the same thing Fourier transform there, and we would like to work with this k and omega. Right? When we do experiments, how we know this is omega is typically 2 pi over t, right? There is some scale time period, and omega is the frequency associated with it, and k is 2 pi over wavelength. That's the same idea, but as of now, I haven't told you what exactly k is and what exactly frequency is, right? So, but before that, so let's see how do we do this. I would like to work with these components, and if I have an equation which is having both sides the same Fourier transform, I can get rid of this integral completely. So let's begin by asking, what is time derivative of the electric field in the time domain? So I'm taking the time derivative. Notice on the right hand side, in the Fourier world, there is no time in this components. Instead, they are all in the exponential. So when I take the derivative, it's bringing down a minus I omega. So let me write this down. So I have not yet operated it. Minus I omega t. But now, when I take the time derivative, there is a minus I omega times the electric field. So that's the key point we want to take care of, and what I'm going to do today is that the message is that in the Fourier space, if I want to go to Fourier space, I change all the time derivatives to minus I omega. And of course, the dependence is in frequency afterwards. Do the same thing for gradient. Now, if I do gradient of the electric field, I don't have to put the dot. If I put the dot in the Fourier space, also I have to put the dot. Or just not to confuse. This is, yeah. So that operation here, again, do the same thing. This gradient operator, it hits the R and the exponential. And it leaves the exponential intact like the time derivative did. And it, instead of R, the coefficient of R is what it brings down. So that brings down an IK. Yeah, with the electric field. So again, the message is that wherever there is a gradient, I just have to replace it with the wave vector when I'm in the Fourier space. Okay, so that's our message here. As far as I'm working with single field quantities, like especially the Maxwell's equation, that's what I have to do. So now let's go back to our Maxwell's equation with that information and see how it looks like. So I go back to the original board, and now I have to go to Fourier space for these equations. So I'll use this transcription. Wherever a time derivative and gradient comes, I'll make it convert that into what does that mean? I'll switch over to the Fourier space by replacing time derivatives and gradient. So the first equation becomes, remember, I times k. I times k dotted with d. Now d is in the Fourier space. That's k omega is equal to rho of k omega. So we're working in the frequency and wavelength space, and suddenly things have become easier because now this is not a gradient operator, no derivatives involved. This is algebraic. It's a lot simpler to analyze, and the same thing with ik dotted with b equal to 0, and same thing there. Ik crossed with electric field this is minus, so minus, but time derivative involves a minus, so this becomes a plus. So it's plus I omega b. And finally, your i's can cancel out in the previous equation. Let's leave it there. Cross with h. And we have minus I omega times d plus j of k omega. Visible? Okay. Okay, so if that is the case, from this point on, in this whole class, I will be working only with k and omega dependence, so I'll stop writing the explicit dependence. So if I do that, so since just for so that everything is in the code, so I'll rewrite that, right? So this is simpler now. D is equal to rho I times k divided with p is equal to 0, and I times k crossed with e is equal to I omega d, and I times k crossed with h is equal to minus I omega d plus j. Okay, so that's what we have. So let's now manipulate this. What can we learn from all this? So let's label them. 1, 2, 3, and 4. Let's do the following. That is 1. Yeah. So let's say we are let rho and j be 0, right? Yeah, we're talking about waves now. So let rho be equal to 0 and j be equal to 0. Remember, when we're talking about a wave, then the sources are very far away, and the light that we're seeing is originating from that, but it doesn't really have to be close to that. So it's very far away. So that means that's set to 0, right? So yeah, so we set that to 0, so that's going to 0, and that's going to 0. Those two terms. That means that K is so first equation implies that K is perpendicular to D, and D is the same as E, right? K is perpendicular to E. And second equation implies that K is perpendicular to D or H. Let's keep D. We also have K crossed E is equal to B. What does that mean? So let's start with third one. So third one implies. So let's start with third one and multiply it with D, right? If you want to third one, start with the third one, and we get, let's dot it with K, let's say. So this is K dotted with K crossed with E is equal to omega times K dotted with B. But K dotted with B is equal to 0. So that's equal to 0. And this is also 0 because K cross E is always perpendicular to K. So that's also equal to 0. So that's correct. That's consistent with what we have before. Let's check the same thing with fourth one. We have K dotted with K crossed with H. And that should be the same as minus omega K dotted with D, right? That's equal to 0 because electric field, and this is 0, and this is also equal to 0. That's also very consistent still. So we have learned only two things, that this is perpendicular. So let's now do cross, right? We did dot. So again, let's start with 3. Right? 3 implies that I get rid of the I, and then I have K crossed with E is equal to omega times K crossed with B. That's good. So what we get is that this is K crossed with the used back cab, and what we get is K times K dotted with E and then there is minus of K squared of the electric field is equal to omega times K crossed with B. Well, that's equal to 0. One of the first term is equal to 0 because K dotted with E is 0. That's the first equation. And what we learn is that minus K squared E is equal to omega times K crossed with B. Same thing, we can start with 4 and let's see what we can learn from there. So let's start with 4. Equation 4 implies similarly that K crossed with H is equal to minus omega K crossed with D. Right? And same idea, use back cab, K dotted with H minus K squared times H is equal to minus omega K cross with D. That's equal to 0 again. So we have minus K squared. Let me convert, since E and D is what we want to write in terms of, let me convert this to D. So remember, D is equal to mu naught times H, right? In both Fourier and mean space as far as we are in vacuum, and D is equal to epsilon naught times E. In vacuum, it doesn't have any issues. So H is B over mu naught. I'll keep it on the other side, so it's minus, and that's an epsilon naught, right? So this is omega. Oh, did I miss something? No. So it's omega, and then there is epsilon naught, mu naught, times K crossed with E. So that's something. Okay, what else can we do? But this is the same equation that we have. This can be compared with our original K cross E, right? So we're going in cycles, it seems like. So we also have 1 or 3, right? 3 is already saying that B is K cross. Let me just use this. Right? So using 3 in this, right? I think so. What do you say? This K. So this is minus K squared times B is equal to minus omega epsilon naught mu naught K cross E using our first equation is just omega times B. Sorry, using equation 3. And this tells us that we have K squared minus omega squared epsilon naught mu naught times the magnetic field is equal to 0, right? There are two possibilities, either the magnetic field is 0 or the quantity in the brackets is 0. If magnetic field is 0, that's a trivial thing we're talking about. There is no fields at all. So this implies that K is equal to omega times so let's say this is K squared is equal to omega squared times epsilon naught mu naught. But remember, epsilon naught mu naught is 1 over C squared. So that's the same as K squared is equal to omega squared over C squared, which we typically write as K equal to omega over C, right? That's the connection between wavelength and frequency for light. So this is the same as 2 pi over lambda is equal to 2 pi over frequency times C. Oh, what happened? No, 2 pi nu, right? So 2 pi times nu, right? Angular frequency is 2 pi times nu. So that gives us lambda times nu is equal to lambda times wavelength times frequency is speed of light, inverse of each other. That's good. But there is one more thing we want to see, and that is that what about electric field and magnetic field, right? Are they perpendicular? Like when we think of it as an electromagnetic wave, they must be perpendicular to each other. And that should be possible to see that. Let's start with 3 and see whether we get that. So let's start with 3 and dot that with the electric field this time. So this is electric field dotted with K crossed with E is equal to omega times electric field dot with E. And what do you do about this? K crossed with electric field. Yeah, so this is 0, right? Isn't that obvious? Yeah, it was right obvious there itself, right? So electric field is perpendicular to K cross E, so that's 0. So that's E dot. That's straightforward too, right? So we have K perpendicular to E, E perpendicular to B, all three. This implies that K, E, and B are perpendicular to each other, or orthogonal. To each other, right? There's one more thing I wanted to show, and that is that what about E crossed with B? So let's also do E crossed with B. Which equation should I use for that? That's what E crossed with B. And we will use this piece in here. So it is the same as K. So E crossed with B is nothing but K crossed with E. And divided by omega. Right? So it's 1 over omega. And I'm using the third equation, 3. I'm thinking of monochromatic wave, and E crossed with B in that has this K direction involved in it. So let's see how we see that. So that's equal to what is this? Up? Yeah, back Havikian, correct? Yes. So this is K over omega times E square, E dot with E, and minus of K dotted with electric field over omega times electric field, but that's 0, right? Because K dotted with E is 0. So this gives us E cross B to be equal to E squared over omega. So, but omega is the same as K times C, right? So let's write this as, K over omega is 1 over C. So this is K hat times 1 over C times electric field square. So that's one thing, but the same thing I should be able to do using K cross H also, right? And I will get a similar equation. So where should I do that? So since you know that this is perpendicular, so let's start the same thing with this equation here. So that's I can do E cross B starting from the fourth equation also, which will be equal to E crossed with K crossed with H, right? I switched the sign E crossed with, what did I do? Yeah, I should have done E crossed with B, but then I switched back. E crossed with B, but then that should have been B on that side. Did I write this correct? No. Wrong, right? Okay. Oh. So E crossed with, so K crossed with H is equal to minus omega epsilon naught times E. So now let's do E crossed on the both sides. So that's K crossed with H crossed with B is equal to minus omega epsilon naught times E crossed with B. So E crossed with B is use the minus sign to bring it on the other side. I'll also use that minus sign to flip back cap so that I can use the back cap. So that's 1 over omega epsilon naught. And then there is B crossed with K crossed with H. Write this H in terms of B. So H is B over mu naught. So that's B over mu naught. Sorry, a few things simultaneously. So that gives me equal to, again, the back cap rule. So the first one is K. So this is K hat or K, vector K, over times C square because of epsilon naught mu naught over omega times B square. And the second piece is 0, right? plus B dotted with K, right? That's it. K over omega again is 1 over C, so that's K hat times C times B squared. Agree? But both are the same. These two are the same, so we learned one more thing. E crossed B is equal to K hat times E square over C, which is also equal to K hat C times B square. That surely suggests that E square is equal to C square times B square. Right? That means that how much ever magnitude of electric field is there, the magnitude of electric field is the same as C times the magnitude of the magnetic field. Right? They have the same strength except for the speed of light. If it is C times B, then it's the same sort of strength. If this also means that the amount of energy stored in the electric field is exactly the same as the amount of energy stored in the magnetic field. Right? When you think of this as your electromagnetic wave, so that's your K, and that's your B, right? So that's electric field, and that's your magnetic field. One could ask how much energy is stored in the electric and what is the fraction of energy stored in the electric and magnetic field, and that's exactly the same. But then you would say, oh, what about the C, right? Is there a C extra in there? No. Why is that? Because so we go back and calculate it further for you, right? What else can I say? How do I know what's the energy? Energy is electric fields. Yeah, energy. Yeah, one way to see it immediately is that electric field. So this is slightly misleading in the sense I'm going to the Fourier space. Now I haven't done it for the energy still, but this is very, at least, this is plus 1/2 times H dotted with E, right? Correct. So if I say that electric field is C times B, what can I learn from this in here. So that's 1 by 2 epsilon naught E square plus 1 by 2 V square over mu naught. So let's call this energy in the electric field. So that's 1 by 2 epsilon E square. And energy in the magnetic field, we will call it 1 by 2 V square over mu naught. And then let's ask what's the connection between the two. So we see that UE over UB is epsilon naught over mu naught times E square over B square, right? Is that correct? Did I write this correct? That's equal to E square over C square E square. In general, this is a true fact that the amount of energy stored in ratio of amount of energy stored between electric and magnetic field is this. But if it is, if you're talking about a monochromatic wave or electromagnetic wave, which is governed by the fact that rho is 0, J is 0, if those two are 0, that means very far away from the sources. This is exactly equal to 1 because we just now derived that E square is equal to C square B square. That implies that energy stored in the electromagnetic or the electric field is exactly the same as the energy stored in the magnetic field. So this should, like, you probably have seen it before, but it might not have been highlighted. This is, you surely know this before. We've learned that. This, you're surely aware of this, except for the fact that you might not have seen this constant in front. You might not have realized that this is actually energy, right? E square is, so if this is E square, so how can I write this in terms of energy? So electric field square is 2 times UE, right? So let's see. If I put it back, since UE is equal to UB, so this is equal to 2 times or U is equal to epsilon naught E square, which is also equal to B square over mu naught, because both are the same. So you should be able to write this in terms of U. So that's K hat times E square is U over epsilon naught. That's U over C times epsilon naught, or you can say that's also good. So it's K hat times, since we know B square, so that's U over times mu naught. Either way, it's okay. So basically, the idea is that E cross B is actually having that U in it. Right? Yes.
You still need a C.
You don't need the C here?
No, in the last one, you do need a C.
You do? Oh, because there's a C
Yeah,
there, right?
right.
Yes, C. C times mu naught. And if you were to think of it as momentum, right? So you want a D. So if you multiply by, so if you multiply this by epsilon naught, so this becomes D, right? So D cross B, I think that's the best way of writing it. So I multiplied by an epsilon naught, so that's K hat times U, and there's this 1 over, so that becomes C, right? So that's the best way. Because D cross B, remember, is momentum, right? So the right way would be that D crossed with B, which is, recall, momentum, right? Momentum density. This will be K hat times U over C. Right? So that's a better way of seeing. So this is this should be new in the sense that at least you know that it's perpendicular but it's actually the energy that's showing up. And the amount of energy stored in electric and magnetic field is identical. Otherwise, most of the things you knew before, right? So in Fourier space, all this comes out very almost immediately.
You can do the same, or similar with the pointing, E cross H, right?
Yes, E cross H will be mu naught times, so let's see, E cross with H. Does that come on, get it better? So that's 1 over C square. So yeah, so that's equal to K C times U, right? Yeah, good. That's nice. Yeah, right. So that's around 1 over C square, C equals that. Good. So those are nice, simple identities we have for electromagnetic waves very far away from the sources. So something that come out very nice. Okay, I'll stop here and I'll see you guys online next time. And have a happy Thanksgiving. You said happy Thanksgiving or please?
Yeah.
Happy, right?